Welcome to the 7th training session of the Data Communications Training Classroom. In the previous session, we discussed the basic concepts of IP routing, including the static route, route summarization, and the route selection rules. We know that static and direct routes contribute a lot to the routing table. In addition to static and direct routes, the routes discovered by dynamic routing protocols are common and play an important role on networks. Today, we will talk about dynamic routing protocols using Routing Information Protocol, RIP, as an example. Although RIP is outdated and rarely used on networks nowadays, it is worth learning. This is because RIP is a typical dynamic routing protocol with simple principles, easy to configure, and is a good introduction to dynamic routing protocols. In addition, RIP is a distant vector protocol, which is an important type of dynamic routing protocol. First of all, let's learn about the basic concepts of dynamic routing protocols. Each router maintains a routing table locally, which contains routing entries learned by the router. Each routing entry is called a route. Each route leads to a network segment or a destination IP address. The routing table works a bit like a map and is necessary for each router to implement data forwarding. To query route entries in the routing table, run the display IP routing table command. In the routing table, the Brodo field indicates the routing protocol of a route. The value can be direct, static, or the name of a dynamic routing protocol through which the route is learned. Generally speaking, routing protocols are classified into three types: direct routes, static routes, and dynamic routing protocols. Direct routes. After an IP address is configured for an interface of a router, the router automatically learns the route corresponding to the network segment of the IP address and adds the route to its routing table. This route is a direct route. Direct routes are like doorways. They can be added to the routing table on the condition that both the physical and protocol status of the corresponding interface is up. Static routes. As we mentioned in the previous training session, static routes are easy to configure. However, each network segment requires a static route. If a network consists of a large number of network segments, the configuration workload is extremely heavy. What's more, static routes cannot dynamically respond to topology changes. To solve this problem, static routes need to be associated with BFD, dynamic routing protocols. In the case of a large network, direct and static routes are far from enough for routers to implement routing. In this case, dynamic routes are also needed. Dynamic routing protocols enable routers to dynamically exchange routes or route calculation information, such as link state information. In this way, routers learn or calculate routes to enrich their routing tables. Next, let's move on to the classification of dynamic routing protocols. There are two classification methods. Based on the routing algorithm or routing information, dynamic routing protocols are classified as distance vector protocols or link state protocols. Distance vector protocols include RIP and BGP. BGP is also a path vector protocol. One of the most important characteristics of distant vector protocols is that each router sends all the routes in its routing table to other routers. Through routes exchanges, each router learns the routes that its routing table does not have. we know that static routes are used locally and are not shared. Once a distant vector protocol is enabled, routers can communicate with each other for routes. In link-state protocols, what routers exchange are not routes, but topology information. Through topology information flooding and collecting, each router builds its link-state database, LSDB, which helps the router to know about the network topology. Then the router calculates shortest path trees, SPTs, with itself as the route. Based on the protocol running scope or usage scenario, dynamic routing protocols are classified as interior gateway protocols, IGPs, or exterior gateway protocols, EGPs. If a dynamic routing protocol runs within an autonomous system, AS, the protocol is an IGP. An AS is an independent and autonomous network set that consists of routers using the same routing protocols and a routing policy and is managed by a technical administration. For example, the network of a company can be viewed as an AS. If the company is an international one, each branch of it can be viewed as an AS. Common IGPs include RIP, OSPF, and IS. If a dynamic routing protocol runs between AS, the protocol is an EGP. BGP is the most common EGP. Distance and direction are the core of distance vector protocols. Routers running distance vector protocols do not know the topology of the entire network except for the distance and direction. The routers use the hop count, which is also called the metric, to measure the distance to the destination. As for the direction, if a router receives a route from one direction, it forwards packets in the reverse direction. R1 sends the route 1.1.1.0/24 to R2. After receiving the route, R2 adds it to the routing table. This route is a direct route of R1. Therefore, the hop count is 0 to R1. R2 learns this route from R1, so the hop count to R2 is 1. RIP is one of the earliest IGPs. It is a typical distance vector protocol and applicable to small-sized networks. RIP is based on UDP, and the port number is 520. The priority of RIP routes on Huawei devices is 100. RIP has 3 versions, RIP 1, RIP 2, and RIP NG. RIP 1 and RIP 2 are used on IPv4 networks, and RIP NG is used on IPv6 networks. At present, RIP 2 is more commonly used than RIP 1. Routers broadcast routes in their routing tables periodically. Now let's talk about how a distance vector protocol works. In a networking, RIP runs on the 3 routers, and they have their own direct network segment. After IP addresses are configured for interfaces on the routers add their direct routes to their routing tables and flood the direct routes. R1 receives 2 routes from R2, 192.168.12.0 and 192.168.23.0. Because the former one is a direct route of R1 adds only the latter route to its routing table. The route 192.168.23.0 is a direct route of R2, so the hop count to R2 is 0. After R1 receives this route from R2, the hop count to R1 is 1. In addition, R1 receives the route through GE 0/0/0. Therefore, GE 0/0/0 is the outbound interface of this route in the routing table. Similarly, R2 learns a route from R1 and another one from R3 and adds the routes to its routing table. In the next flooding period, each router floods the routes in its routing table. After the route flooding, R1 learns from R2 the director route 3.0.0.0 of R3. To R1, the hop count of the route is 2. Similarly, R3 learns from R2 the director route 1.0.0.0 of R1. To R3, the hop count of the route is also 2. In this way, the three routers obtain all routes in the topology and have the same understanding of the entire topology, and the routes reach a stable state. Now, let's talk about the RIP route metric. The metric is also called the cost and is displayed in the output of the display IP routing table command along with the other route information, such as the protocol and priority. In RIP, the metric refers to the hop count of a route or the number of routers along the path to the destination. The hop count from a router to its directly connected network is 0, and the hop count from a router to a network that is reachable through another router is 1. The rest may be deduced by analogy. The smaller the hop count, the better, because the destination is closer. In the figure, R5 sends its director route 100.0/24 to R2 and R4. After R2 learns the route, the hop count becomes 1. After R1 learns the route from R2, the hop count becomes 2. After R1 learns the route from R3, the hop count becomes 3. Because 2 hops is less than 3 hops, R1 selects the route learned from R2 to forward the traffic designated for 100.0/24. However, the bandwidth of each link on the selected route is 1.544 megabit per second, whereas the bandwidth of each link on the other route is 1 gigabit per second. Obviously, the other route is better because it has a smaller possibility of congestion. Despite this fact, RIP cares only about the hop count when selecting the optimal route. This is one of the reasons why RIP is eliminated. As we just mentioned, to check the route metric, run the display IP routing table command. We use the routing table of R1 as an example. R1 learns the route 192.168.23.0/24 through RIP, so the proto field is RIP. The priority of the RIP route is 100, and its metric is 1. Each routing protocol has a priority. In most cases, the routing table of a router consists of various routes obtained through multiple routing protocols. If some routes are destined for the same network segment, but are learned through different routing protocols, the router compares the priorities of these routing protocols and selects the route with the highest priority. For example, RIP runs between R1 and R2, and OSPF runs between R2 and R3. R1 sends its director route 1.1.1.0/24 to R2 through RIP, and R3 sends the director route to R2 through OSPF, facing two routes that are destined for the same network segment, but are learned from different protocols. R2 compares the priorities of the two routes. On Huawei routers, the priority of RIP is 100, and the priority of OSPF is 10. Note that the smaller the priority value, the higher the priority. Therefore, R2 selects the route learned through OSPF. The priority of a routing protocol may vary by manufacturer. On Huawei routers, the priority of routing protocols are listed in this table. Director routes have the highest priority, with the value being 0. The priorities of OSPF internal routes, OSPF external routes, is routes, static routes, and RIP routes are 10, 150, 15, 60, and 100, respectively. RIP updates routes based on hearsay. After a router receives a route, it adds the route to the routing table if the routing table does not have this route, and then floods the route. Because RIP updates routes based on hearsay, routing loops may easily occur. For example, 3.0.0.0/8 is a direct network segment of R3. If the route to the network segment fails, R3 deletes the route from its routing table. R2 floods its routes to R3. After R3 finds the route 3.0.0.0/8 among these routes, it believes the route available and adds the route back to its own routing table. It then changes the hop count from 1 to 2. R2 is connected to a PC, and the PC has packets destined for 3.0.0.0/8. So it sends the packets to R2. After receiving the packets, R2 queries its routing table and forwards the packets to R3 through GE0/0/1. After R3 receives the packets, it queries its routing table and sends the packets back to R2, which causes a routing loop. As the route is flooded back and forth on the network, the hop count keeps increasing. The reason for the routing loop is that RIP does not know the network topology. There are a lot of functions to prevent routing loops, including the maximum hop count, split horizon, route poisoning, poison reserve, hold down timer, and a triggered update. Next, we will explain some of these functions. As we have mentioned, the hop count keeps increasing once a routing loop occurs. To prevent the problem, RIP sets the maximum hop count to 15. Any route with a hop count greater than 15 is regarded invalid. However, if a router on the large network receives a route whose destination is 16 hops away, the router considers the destination unreachable. This is why RIP cannot be used on the large-scale networks. Now let's talk about split horizon. For example, A tells B a funny joke. If B tells the joke back, which is similar to a routing loop on the network, it will be extremely weird and awkward. In this situation, it would be better for B not to do so. Split horizon has a similar function. Split horizon prevents RIP from sending back a route through an interface that received the route. For example, after R2 learns the route 1.0.0.0/8 from R1 through GE0/0/0, R2 will not send the route back to R1 through this interface. This prevents routing loops. Next, we talk about route poisoning through an example. After R3 finds the network segment 3.0.0.0/8 unreachable, it sends to other routers a root update message, with the hop count being 16, indicating that 3.0.0.0/8 is unreachable. After receiving the message, R1 and R2 update their routing tables. Now, let's move on to the next anti-loop function, poison reverse. According to Split Horizon, RIP cannot send a root back through the interface that received the root. In poison reverse, RIP can do so, but the metric of the root is changed to 16. Poison reverse and Split Horizon are mutually exclusive. You can select only one of them. There is a book that I would like to recommend to you, Routing TCP IP Volume 1. When describing the difference between poison reverse and Split Horizon, the book is cited as saying, "Bad news is better than no news." Compared with RIP1, RIP2 has more advantages. RIP2 supports external root tags and can use tag-based routing policies to flexibly control routes. RIP2 packets contain mask information. Therefore, RIP2 supports route summarization and classless interdomain routing, CIDR. RIP2 supports next hop specification so that the optimal next hop IP address can be specified on the broadcast network. RIP2 uses the reversed IP address 224.0.0.9 to multicast update packets. Only the devices that support RIP2 can receive RIP2 packets, which reduces resource consumption. RIP2 supports protocol packets authentication, which enhances security. Last but not least, let's talk about RIP configuration. To deploy RIP on the device, perform the following operations. First, run the RIP process ID command to create a RIP process. The process ID parameter is optional. If no process ID is specified, RIP process 1 is created. Second, run the version num command to specify the RIP version. Version 2 is recommended. Third, run the network address command to enable RIP for a specified network segment. For example, a router has two interfaces. The IP address of one interface is 192.168.12.1/24, and the IP address of the other interface is 192.168.23.2/24. If you want to enable RIP on the former interface, run the network 192.168.12.0 command. After RIP is enabled on the former interface, this interface floods the routes in its routing table. In this configuration example, the IP address of PC1 is 192.168.1.1/24, and the IP address of its gateway is 192.168.1.254. The IP address of PC2 is 192.168.2.1/24, and the IP address of its gateway is 192.168.2.254. RIP2 runs on R1, R2, and R3. It is required that the two PCs communicate with each other. On R1, run the RIP1 command to create RIP process 1, then run the version 2 command to set the RIP version to 2. Finally, run the network 192.168.1.0 command to enable RIP on the interface connected to PC1, and the network 192.168.12.0 command to enable RIP on the interface connected to R2. Configurations on R2 are similar to those on R1, except that RIP is enabled on two different interfaces, one connected to R1 and the other connected to R3. Configurations on R3 are similar to those on R1, except that RIP is enabled on two different interfaces, one connected to R2 and the other connected to PC2. After all the configurations are performed, we can run the display IP routing table command to check the routing table of each router and test whether PC1 and PC2 can ping each other.